All right. Well, welcome everybody to this edition of the Geometry and Model Theory Seminar at the Fields Institute. Today's speaker is Belotto da Silva from Marseille. And he will talk about a new proof, or at least a new version of a proof, of Gabrielow's rank theorem.
Right. So thanks a lot. First of all, thanks a lot to Patrick for the invitation and the opportunity to talk, and everyone that is there. I have the chat open if anyone wants to make a remark or a question. So I'm going to talk about a new proof of Gabrielov's rank theorem. I'm going to tell a little bit about it. So this is a work. This is a work in collaboration with Octave Cormier, which is a postdoc in Budapest, who was a postdoc here in Marseille, and now is a postdoc in Budapest, and Guillaume, that is a colleague here from Marseille. So just maybe before starting the talk, I just wanted to say a couple of words about the work. So I'm going to talk about a result, a theorem that was originally proved by Gabrielov in the 70s. And the original proof is considered to be very difficult. So you can trace this in the literature. There are interesting results in the 80s and 90s where the authors they prove sometimes weaker versions of the result, reprove weaker versions of the result that they need, and they do say that the original proof is very difficult. So just to give more elementary proofs, and the only other proof in the literature is the proof of Dugeron, that I'm going to come back to it. And so we started our project trying to understand the proof ourselves and trying to clarify the proof and to transform some of their ideas into statements which we probably used elsewhere. And besides that, we have developed we extended the result to certain, we look into extensions in commutative algebra and other kind of result. But the main focus of my talk is to try to talk about the proof itself. So this is going to be my main focus. Which means that the talk, I'm going to try to make it not so technical, but I'm going to jump into the proof quite quickly. I'm going to sacrifice a little bit the connected topics and applications of the result, and I'm going to jump much more into the proof itself. I want that everyone gets out of the meeting, of the seminar, having the feeling that they understand that at least heuristically the ideas of the proof. So this is kind of the plan, the strategy for today's talk. Okay, so why is not moving? Yes, okay. So just preliminaries first. So what are the kind of result that we are interested in? So I'm going to denote by K a field, so either the real or the complex numbers. And a priori, I'm going to consider some analytic germ, some a morphism of analytic germs like this, from Qm to Qn, that sends 0 to 0. And I recall that, so just given as it's written here, and I recall that phi always induces the morphism between power series. So it's the pullback, right? So I have the ring of analytic series of the convergent series, sorry, in the target, which is sent to the ring of convergent series in the source, just by taking the pullback of it, just by taking the composition. And for here onwards, U is always going to be a variable which is in the source, and X is always going to be a variable which is in the target of the geometrical morphism, and the other way around for the pullback, right? X is in the source of the phi star, and U is going to be in the target of phi star. There is this double thing. And Gabrielov's rank theorem is a theorem about the image of phi. So what we're interested in understanding is, to a certain extent, what is the dimension of the image of phi of this germ here. So what do I mean by that? So I can mean two things. So already if I'm thinking of it in a geometrical term, I can look at the image, the set which is given, and generically this is going to be a manifold. So we can think of this in the following way. We can look at the Jacobian of the morphism. And if the Jacobian is, say, invertible, if n was equal to m, we have the inverse function theorem that will say that actually the function is invertible, so the image is going to be locally everything. And more generally, even if n and m is not the same, but you have some rank which is constant on an open set, then I have theorems, classical theorems of differential geometry that will say that the image is going to be a submanifold of a certain dimension, which is equal to this rank of the Jacobian. So in here, we want to define the same thing, but we want to do it generically. So we don't want to add the hypothesis that the rank is actually constant and maximal over an open set. We just wanted some rank in some notion of rank which is maximal in an open dense set close to the point. So this is basically the definition of what we're going to call the generic rank, which is going to give us the generic the dimension, the geometrical dimension of the image, right? So if this Jacobian here is just the rank of the Jacobian of phi, and I'm taking over the fraction of QU, this is just a way to think of this as the maximal rank in terms of the power series in U. Okay, so this basically, if I look at the image and I take away some set of small dimension, it's going to be it's going to become a submanifold, and this is the dimension of this submanifold. And the other kind of dimension that I'm interested in looking, we're interested in looking, is the analytic closure of the image. So in order to look at the analytic closure of the image, we're going to look at the ideal that generates this analytic closure, right? So what I'm going to take is all f's which are in the target, all functions f which are in the target, such that when I compose with phi, this is 0. So of course, these guys, they are containing the analytic closure of the image, because definitely they are going to be 0 over the image of the phi. And since I'm taking all of them, this is actually the analytic closure itself. So this is the kernel of phi star is going to give us, it's the ideal that gives us this analytic closure. And therefore, the rank, the analytic rank that we're going to consider is the dimension of the analytic space generated by this. So this is the analytic space is not the dimension of the kernel as a crude dimension, but it's of the quotient, right? You have this ideal here containing embedded in an analytic space. So the dimension of the quotient, in the crude dimension of the quotient, is going to give us the dimension, the analytic dimension of phi, right? It's going to give us the dimension of the analytic set containing, the smallest analytic set containing the image. So just by these two observations, I know that the generic rank is always smaller or equal than the analytic rank, because it's going to be, generically, this is a submanifold. I'm not taking anything which is bigger. The analytic rank certainly contains the image itself. Okay, so these are the two kinds of rank that I'm interested in looking at, and just some classical results that we have in mind. So if we are thinking of phi as a polynomial or algebraic, then we actually have that the two ranks are equal. So we do have a result like follows from the result of Chevalier in the complex case and Tarski in the real case, the two ranks are going to be equal, right? Actually, they are not necessarily, we all know that it's not necessarily true that the image of the map is going to be analytic itself. It might be semi-analytic, well, in this case, semi-algebraic, but its dimension, its closure is going to be of the same dimension. Another related result that I have chosen is Römer's proper mapping theorem from 58, that states that if we have a proper analytic morphism between complex analytic spaces, under the assumption that Y is reduced, then the image itself is an analytic space. So the image itself is an analytic space means, in some sense, that the two ranks are equal at every point. The analytic closure is the set itself. But in the case of analytic germs, then the situation is different. There is already an example from Osgood from 1916 that claims that there exists a morphism from K2 to K3 such that the generic rank is 2, but the analytic rank is equal to 3. That is, if I take the closure of it, I'm going to have all of the set on the target. I'm going to have K3. So more precisely, what is this example? Just so that we build some intuition in it. It's an example that goes from C2 to C3. We can go from R2 to R3, it's going to be the same. And that sends U and V to U, UV, UV, exponential V. So one of the things that I want to note, and just to build up an intuition for the next slide, is that the function that would annihilate phi, the function that would make it 0, that would do this, would be a function of this form here, x3 minus x2, exponential of x2 divided by x1, right? Exponential of x2 divided by x1, this is v, so this is the exponential of v, and then x2 is just u times v, and x3 is what we are trying to, well, uv exponential of v. So this expression here would mean that the morphism is 0. But the thing to notice is that f is not analytic, and it has an essential singularity. So even if I look at the formal Taylor expansion of this function here, it would not give us a formal power series. It would be a Laurent series with an infinite number of denominators. So you cannot even have some sort of formal power series that annihilates this morphism here, right? So this gives us some sort of intuition, which was from the time. And therefore we have that the generic rank is 2. The set in the image is going to be of dimension 2. It's contained in this graph here, as we could say, with the closure at x1 equals 0 here, a little bit different. But the analytic rank, there's no analytic function which composed with phi is 0. So the analytic rank is 3. If I take the analytic closure, give me everything. So the previous comment leads to some sort of a question of Grothendieck about the relation, okay, maybe not with the generic rank, the geometrical one, but with the formal one. So given this kind of morphism, an analytic morphism, we can always consider its completion, right? Not from the complete formal power expansions. And, be the expansion of phi. Okay, so very good. So the formal rank is going to be defined exactly the same as the analytic one, but now the ideal that we're considering is the ideal of all functions, formal power series functions, which when composed with phi are 0. So this is, if we want to have some intuition or geometric intuition, is like the formal variety that contains it. It follows kind of from elementary, from this kind of heuristic about the geometry of what is the formal, that it's not difficult to convince oneself, it's harder to prove it, but it's not difficult to convince oneself that you have this kind of inequality. The generic rank is always smaller or equal than the formal rank, which this one is easy to see, is smaller or equal than the analytic rank, because every function which is analytic, which annihilates phi, its power series will also annihilate phi. So this leads, there is a very close connection between formal power series and analytic functions, and analytic series, convergent power series. So is it true that the formal rank is always equal to the analytic rank? So if I have some formal power, some formal variety which contains my image, does it converge to a certain degree? So the first result of Gabrielov, which I'm not going to talk much, which it's actually very, at least was considered surprising at the time, is that the answer is no, actually. There exists actually a map from C2 to C4 where all of the 3 ranks are different. So this is the first result of Gabrielov. And then he does give a positive answer to the problem of knowing when the generic rank is equal to the analytic rank. And this is what we're going to call Gabrielov's rank theorem. So it basically states that we have our analytic map. And if the generic rank is equal to the formal rank, then all of the 3 ranks are the same. So this gives us some sort of characterization, right? We characterize morphisms which have these 3 properties, which is a quite desirable property. It means that the analytic morphism does share some, the image of it at least, does share some properties with the algebraic category. We can work to a certain extent. We have to make this precise in case by case, but we can heuristically imagine that it's going to have behaviors close to the analytic, to the algebraic one. So a couple of comments before diving more into the theorem. The results also holds true for complex analytic morphisms of this form. So it can be singular analytic spaces as long as the image is reduced. We're not going to talk about the general case in the talk. I'm going to focus on the one that is non-singular. And we can also reduce the real analytic statement to the complex analytic statement by considering a complexification. So from now on, we're going to only look at k equals to c. So these 2 remarks I won't explain much more, but it's just elementary considerations. We can do these things, right? For just maybe one comment for the single analytic spaces, the difficult thing to do is to extend the notion of generic rank. Analytic rank and formal ranks are quite direct. They are coming from commutative algebra, so they're quite direct to extend. Fair enough. Now, just a couple of words about the history and interest. So the original proof of Gabrielov from 73 is the proof that I said that is considered very difficult. Later in the 90s, there's the proof of Tougeron, which once again, for different reasons, is still considered very difficult. And in our new result, our new preprint, we are trying to clarify this proof in between other things. So this is the third result in the literature that tries to, or that provides a new proof of the Gabrielov ring theorem. This is a theorem that is connected with a lot of other topics of research, although I'm not going to talk much about the interest and connected problems. I just wanted to say that there are several. So there are several papers about study of map germs, Eakin and Harris, Izumi. This is connected with problems in foliation theory, so especially about convergence of first integrals. So this goes back to a result of Malgrange about the called singular Frobenius theorem, and the use that Servoff-Mattei do it in the 80s and later on even. This has a connection with subanalytic geometry, going back to results of Bierstein-Schwarz, Bierstein-Millman, and especially with works of Pawłowski too. And also the cases where the map does not satisfy the conditions of Gabrielov. The map is not regular in the sense of Gabrielov. Then we do have some interesting counterexamples in the real analytic category, exactly because you don't have the same properties that of algebraic maps. So you have results of Pawłowski, Bierstein, Paruzinski, and myself with Bierstein, recent counterexamples in real analytic geometry. Okay, so this is what I would like to talk about history and interest. And I'm gonna jump into the idea of the proof now. And the first thing that I want to do is to kind of separate one particular case, which is historically considered a difficult case. So this is actually the low dimensional rank. So it's the same statement of the theorem. The only difference is now we go from C2 to C3. That's it. We have that the generic rank is equal to the formal rank equals to 2. And we want to prove that the analytic rank is 2. So just to get a good feeling of what it means, to get some grasp of the objects that we have, if we have the formal rank equals to 2, this means that there exists one formal power series which annihilates the morphism. So the kernel of phi star is generated by some function. By formal Weissel's preparation, we can distinguish one variable, say y. So we can actually suppose that the generator of the kernel is actually a polynomial in, say, y, with coefficients, formal coefficients in x, x1, x2 here, to some degree t. We can also suppose that it's irreducible, and therefore our goal, once we have this setting here, our goal is to show that P is convergent. If P is convergent, certainly the analytic rank is 2. And if the analytic rank is 2, then any generator of it has to be divisible formally by P. So this gives us some sort of unicity here. We have to show, our goal now is to show that this P here is convergent. Now, before I turn into to jump into the proof of the difficult case, I want to make a couple of remarks about how the general case, I'm going to focus much more on the difficult one, on this low dimensional one. But before doing so, I want to make a couple of remarks about how the general case comes to this low dimensional case. So just the structure of the proof, like, you know, the heuristic, not heuristic, but just the far away structure of the proof, right? The structure of the proof is a proof by contradiction. So we suppose that there exists a morphism from Cn to Cm, such that the ranks, the generic rank, the geometrical one, is equal to the formal one. This is bigger or equal to 2, but the analytic rank is strictly bigger than the formal rank. So we suppose that the Gabrielov ring theory is not true. There's a comment here. Why am I supposing that it's bigger or equal to 2? I'm supposing it's bigger or equal to 2 because in the case that is equal to 2, so it's like the image is like a curve, then we can actually prove this in a direct way via quite elementary methods, and the proof is not going to shed any light in the proof of the general case. So I'm actually just supposing already that we are in the case that the 2 ranks are bigger or equal to 2, but just so that we keep in mind that the case that they are equal to 1, we don't even need this hypothesis. The case equals to 1, we just need generic rank equals to 1, and then all the ranks are equal to 1. It's much simpler. So, okay, so we put ourselves in this kind of situation. And by making allowed operations, so I'm going to be a little bit more precise about what allowed operations are in the next slide. But just to keep in mind, these are operations in the source or target that allow us to keep control on the rank, on the 3 ranks. I'm going to be a little bit more precise in the next slide. So in the source and target, so we make these allowed operations, we show that there exists a morphism from C2 to C3, such that, again, the generic is equal to the form equals to 2, but the analytic one is equal to 3, exactly because of this, right? It has to be equal to 3, it cannot be bigger than that. And this is what we're calling the difficult case. Finally, the proof of this difficult case, which will come afterwards, is direct. Now, a couple of remarks about this passage here, from the general case to the low dimensional one. The first remark is what we are calling these allowed operations. So these allowed operations, for example, are of the following form. We have some morphism here, K analytic, and if we consider some blowing up, local blowing up, a quadratic transformation, or a power substitution in the source, or a power substitution in the target, then the ranks of this new morphism, the composition of it, does not change. So in the previous slide, we can make transformations of this morphism by preserving all of these 3 ranks if we just make blowings up or power substitutions in the source or power substitutions in the target. Now, the first warning here is that blowings up in the target do change the rank. So this is the kind of thing that we need to avoid. Now, the general case, we won't use blowings up in the target. So all arguments for us are going to be the local. In the low dimensional case, what we're calling here a difficult case, we will perform blowings up in the target. So the arguments become global. So this already gives an heuristic why this case here, the low dimensional one, is actually going to be harder than the general case, the reduction from the general case to the low dimensional one. The second remark is to give an idea of why n equals 2, why that particular case from C2 to C3 is the difficult one. So I'm going to consider, just to illustrate the difficulty, some morphisms here that I'm calling phi n, that goes from Cn to Cn plus 1, where the generic rank is equal to the form 1 equals to n, and the analytic rank is equal to n plus 1, so everything. And just as before, I can imagine that the generator of the formal ideal here that annihilates phi n is just some irreducible polynomial, like this one. But now the AIs are formal power series in x1 to xn. And this is our generator. So we are exactly in the same situation as before. For every n which is bigger than 2, if n is equal to 2, we're exactly in the same case as before. And what we're going to do is some sort of reduction in the dimension. So if n is bigger or equal to 2, bigger than 2, sorry, strictly, then we are going to restrict the morphism to a sufficiently generic hyperplane H in X on the target. So we look at the target and we restrict it to this hyperplane. And then we're going to have this morphism phi n minus 1, which is just the restriction over the preimage of H. Oops, sorry. And what we're going to prove is that the generic rank in this case is going to be equal to the formal rank equals to n minus 1. And the analytic rank is going to be n. So what we're going to do is that we're going to cut it with a hyperplane section, and we're going to obtain the same kind of situation, but now with n minus 1. Now, there are 2 points here which are of interest. The first one is, in general, there's no reason for this preimage here to be of the form Cn minus 1. It could be 0 only, even for a generic hyperplane section. So this is not true for any morphism. We actually need to do some sort of preparation before. This is done via allowed operations, and so there's a step about preparation of morphism, but this is not something that depends on the dimension n here, on the n. So this is something that I'm going to not talk in the talk. This comes from an original idea of Gabrielov already, but we're not going to talk in the talk. I want to focus on why the idea here breaks for n equals to 2. And the reason is because of the tools that we use. So first of all, if H is a sufficiently generic hyperplane in X, we have a theorem of Alenka that says that, well, if P is divergent, then its restriction is divergent. So this is already good because, okay, we are taking the restriction of P to this hyperplane section. Is it still going to be a formal power series which annihilate this restricted morphism? So we do know that the generic rank is equal to the formal rank equals to n minus 1, but also knowing that it's divergent means that the analytic rank could not drop. Now, the problem with this idea is that we do need another result. We do need what we're calling the formal Bertini theorem, which is proved by Shaw in 58, which states that if n is bigger or equal to 3, then it's not only true that the restriction is divergent, but if it was irreducible, as it was, then the restriction is again irreducible. Now, this theorem fails for n equals to 2. So we just take this example here, a simple example. Say you take x2 equals 0, and then you have y minus x1 times y plus x1. So it's not true anymore. So we do need the n bigger than 3. And what could happen is that now our p here restricted to h becomes the product of, it's not irreducible anymore, it becomes the product of two factors. And although everything is divergent, one of these factors could be convergent. And if that was the case, then the analytic rank would drop. So here the key point now that is going to appear for us is this notion of being, even if we start with something which is irreducible, we're going to pass to something which is not irreducible, which we can't factor. So this is going to be a key point in what comes next.
May I ask more questions? What is a sufficiently generic? What does it mean,
right,
sufficiently?
Right, so for each theorem, for each one of the theorems, you have a different notion of what sufficiently generic is. So for a Biancamo, is really very, very, very broad. It you basically just need. Okay, so I don't remember what is the optimal, but if it is some hyperplane which is chosen in a set of positive measure in the set of possibility of in the projective space, you have this result. You just have to have positive measure.
Okay, yes, please. Sorry.
Oh yeah, and by Shaw, you just need it to be outside of a countable number of hyperplanes.
Okay, but in any case, again, with your allowed operations, you can get.
You can build up to the point that this is going to become it's going to become generic.
Okay, thank you.
Okay, so there's no. Okay, so let me pass for the low dimension again, and thanks for the intervention. Any question, please go ahead. So here's again the situation that we want to prove. We are going to pass now from C2 to C3. I'm going to be more specific about it, this case from now on. We have that the generic rank is equal to the formal rank. We want to prove that the analytic rank is 2. So recall, we have this formal power series here, this formal power series, which is a polynomial in Y. And we want to prove that it's going to be convergent. So the first thing that I want to do is to kind of provide some framework where these two remarks can be taken care of. So I want to have some sort of geometrical framework. The proof that we're going to do is going to be using blowings up, as I said, and blowings up have many points in the fiber. So it's already good for us to have some more geometrical framework, not only talking about local rings anymore, but to specify where these rings are in terms of the ambient space. So we're going to take some point A in C2. We're going to denote by OA. I'm going to take out the C2 here, the ring of power series of germs over A. Power series, no, sorry, of analytic germs over A. And the polynomial P that we were looking at, it's nothing else but a polynomial in Y, whose coefficients are in the completion of this ring. And what we're going to take is, we're going to consider finite sequence of blowings up. So we're going to denote it like this. Sigma n F is going to be now the new variety n. F is going to be the exceptional divisor that we're considering. So it's going to be a simple normal crossing divisor. And given any point B in F, which is therefore in the pre-image of A, we can consider the pullback of the formal power series by sigma at this point. So for HB, there's a different one. So the idea is that, okay, the pullback of sigma localized at B is just a morphism from the completion of A to the completion of B. It's just the pullback. You take any function in A and you compose it with sigma localized at B. So therefore, I can define what is the pullback of B just by using this morphism here. And note that I'm not touching the variable y. The variable y in this case here is just being transformed into y is going to be equals to y. I'm just transforming the coefficients of the polynomial. So this is the remark that I'm doing here. I'm never touching the variable y. I'm only transforming the coefficients of the polynomial that we are interested in. This is kind of the operation we're going to div, and this is the kind of thing that we have to do over all points B in the preimage of A. Okay, we're going to work usually with any point B in the preimage of A, or with some point C with a special property in the preimage of A. And the warning that we have from the previous slide, from the second remark, is that even though if P is reducible, this pullback here might not be reducible. It might factor out. So our proof is going to be by induction on the number of blowings up that we're considering. So there's going to be a number of blowings up here coming from the sigma. So one of the first things that I want to exchange is that I don't want to work anymore with irreducible polynomials, but I want something that is preserved by blowing up. So I'm going to use with reduced polynomials. So this is preserved by blowing up. And what we're trying to get is what we are going to call a convergent factor. So this is just some factor of the polynomial, of the formal polynomial, but some factor which has coefficients which are analytic, which are convergent. The rest might be divergent. We don't mind too much, but it's going to be convergent if we have this factor Q. Non-trivial, of course. The degree of Q has to be bigger than 0. So standard remark, if P is reducible and admits a convergent factor, then P is convergent, right? So in the end, that's what we're going to use. We're going to trace back convergent factors. So I'm saying that we have some sort of induction. So this induction will have a base case and an induction step. So what is the base of the induction? So a first result about a preliminary case. We start by considering the case that the degree of P is 1. So if the degree of P is 1, then we have P is written as this nice looking form here, y plus a0 of x. And since it's the generator of the kernel of phi, we do have this nice equation here where a0 is, to start with, just a formal power series, but phi1, phi2, and phi3 are all convergent. Now, without giving much details, what I can say about the truth is that by doing some allowed operations, I can suppose that phi1 is u and phi2 is u times v. And in this case, if a0 composed with u times and u times v is analytic, then it becomes a very simple exercise to show that a0 was itself convergent, is itself a convergent power series. It becomes elementary. And this is the second last slide that I'm going to talk about the morphisms phi explicitly. Now, the base of the induction, the real base of the induction, is the case of quasi-ordinary polynomial. So what does it mean? It means that the discriminant of the polynomial is monomial. So it has this form here, x1 times x2 times a unit. So in this case, we would have the classical Bianca-Young theorem that gives us precise way to describe the roots of this polynomial. So the polynomial now becomes a product of Ci, which Ci are formal power series, composed with some ramifications of x1 and x2. So you have this very precise way of describing the roots of P. And we can conclude in this case that P admits a convergent factor. So how do we do that? So just to keep in mind, if we had done a power substitution in x1 and x2, then we could assume that k is equal to 1. If k is equal to 1, then we are in the situation of the previous slide. So at least one of the Ci is convergent. And the transformation that we did, this power substitution, is cyclic. The group of automorphisms of it is cyclic. So from it, we can come, it's a finite morphism. So it's easier to say like that. It's a finite morphism. So by using standard commutative algebra, we can actually show that the original P before making the power substitution already had a convergent factor itself. So here we are using the previous slide. So notice that we don't even have to, since we're using the previous slide, we don't even have to talk about the morphism itself. Now, there's just a warning about this. So just to say that things are more complicated than what I'm saying here in this slide, because we assume that the discriminant is monomial with respect to a convergent coordinate system. The x1 and x2 are convergent. So I can do this change of variables, this power substitution, and everything is kept kind of, so I can use the previous slide, etc. In the general case, this is not true, but we can treat it. It's just a technical difficulty, an extra technical difficulty that I won't talk about in the talk. Just to keep in mind that there exists technical difficulty, this technical difficulty more. Okay, so what is the overarching inductive framework that we have? It's going to be the following. We're going to take a point A in C2, this polynomial P, which we want to show that is going to be convergent. So since it's going to be by induction, we're going to only suppose that it's reduced. And we're going to consider a sequence of point blowings up, such that the pullback of the discriminant, which is what we needed for getting a Bianca-Young, is monomial at every point. Now, the discriminant of P is a formal curve. It admits a resolution of singularities by formal blowings up. Fortunately, everything is in dimension 2, so formal blowings up of points are actually convergent blowing ups of points. So this does exist. This always exists. For any P that we are considering, we always have the sequence of blowings up as written here. And for this induction scheme, which I won't enter in such detail, we don't only do it in the number of blowings up, but also in respect to the history. So it would be convenient to have this notation. It is convenient to have this notation, FRJ. So FR1 is the exceptional divisor that appears after the first blowing up. And FRR is the exceptional divisor appearing after the last blowing up. And so on. So we have this history of the exceptional divisor. So the induction is done in both in R and J, as we're gonna see. So the induction scheme, let's say like that, is that under this overarching framework, we're gonna assume that there exists some point C, such that PC, the polynomial P pulled back to C, has a convergent factor. And we're gonna prove that P admits a convergent factor itself. Notice that the proposition does not depend on the morphism anymore. So we are not, after this slide, we don't need the morphism anymore. So what is the proof of this difficult case? It reduces easily to the proposition because we have the sequence of blowings up. We have our exceptional divisors F, and we can conclude that, we have the morphism phi1, phi2 going to this point. Phi3 is sent to the variable y. And we can complete the diagram using the universal property of blowings up and resolution of singularities in such a way that now we have another analytic morphism coming here. But now we do know that the discriminant of P is monomial at every point. So by the base of the induction, you just take one point in the image. There's at least one point in the image of this phi tilde morphism, say C. And by the base of the induction, it does admit a convergent factor over that point. So now the difficult case really becomes just this proposition here. Now the main tool to prove that proposition, an inductive proposition, is what we call a semi-global extension result. So again, under that framework, that special framework, we're going to assume that there exists a point C in the first exceptional divisor that appeared. So we have, again, we have this historical thing, FR, which is the full exceptional divisor, and then you have FR1, which is the strict transform of the first exceptional divisor that appeared. And I'm going to assume that the C appears after this, already in this FR1. And that so that the PC has a convergent factor. Then what we're going to prove is that actually there exists an open neighborhood of the exceptional divisor, of this divisor, and a convergent polynomial everywhere there, defined on this open set, such that this polynomial is actually a convergent factor of P at every point along this divisor here, FR1. Now, there is a choice here to be made because of time constraints. And this choice is that I'm not going to give details about how this result the semi-global extension implies the induction, this proposition, induction scheme. This is a choice that I'm making for time constraints. The proof is not trivial, but it's elementary. It's an induction procedure in this history. And I would prefer, by this choice, to talk about this result, the semi-global extension. How do we prove this result? This is where we have kind of new technical difficulties. So I'm going to not talk much more about how to get the induction scheme. Okay, I can come back to this first question later on. So from now on, I'm focused on this result, this semi-global extension result. And in order to prove it, we're going to have basically two main steps. So we're going to first have some sort of Newton-Puiseux-Eisenstein parameterization. So I'm going to talk about projective rings and a Newton-Puiseux-Eisenstein theorem. And then what we're calling local to semi-global convergence of factors. So we're going to talk about projective convergent rings, local to projective convergent factors, and semi-global form extension. So these are kind of the five big steps in the proof. And these techniques, they are all inspired by the work of Tougeron. So they are formalized in a different way, but they are inspired by the original work of Tougeron, not of Gabrielov. At least maybe it appears in the work of Gabrielov, I must say, but we thought about it from the work of Tougeron, by reading the work of Tougeron. So just to give an idea of what we're searching, what is the intuition of what we're searching? So we are searching some sort of subring of the algebraic closure of CEX, which at the one hand, it has to be big enough so to capture factors of P after one blowing up. So we want to have some sort of factorization like this, where these QIs are Ry here, sorry, Y, polynomials in R with coefficients in R, and the polynomial in Y with coefficients in R. So there's a typo here. There's something missing. Such that the QI are global factors along the divisor. So I really want to capture, I'm going to go back 2 slides. I really want to capture this factors Q a priori. So before making any blowing ups, I want to find a ring which all of these Qs that are going to be convergent along the entire divisor, and they're going to factor the polynomial P over the entire divisor, not only over a point, they appear. So in particular, I cannot use the original ring because this is too small. P might be reducible, but it may convert, it may have several factors after one blowing up. So this is too small. And on the other hand, it has to be small enough so that we can manipulate, constrain the elements that appear in it. So of course, we could always try, if we just trying to find a big enough, then we can always just take the algebraic closure. So we're certainly going to have this factorization. And it's not only going to describe things after one blowing up, but after 2, 3, any number of blowings up that we want. But we won't have constraints on the factors to be able to work with them. So we have this kind of 2 ideas here. We have this sort of game to play between something which is big enough or small enough. So this, just to keep in mind this idea throughout the rest of the slides. So, okay, so what are the ring, where is going to be the ring that we're searching? First of all, we're going to look at the ring of valuations. So I'm going to take the valuation of the x-adic valuation of Cx. So this is just the order. And we're going to consider the ring of valuations. So f divided by g, where the order of f is bigger or equal than the order of g. And actually its completion is going to be quite important for us. And the remark here is that after one blowing up, why do we take this ring? That after one blowing up, then if I take the pullback, then I'm going to have u to the power of the order of f divided by u to the power of order of g. So order of f is bigger than the order of g. And this is going to be a well-defined power series everywhere outside of the strict transform of g equals 0. So at least generically along the divisor, this is well-defined. The second thing that we're going to need is that we are going to need some sort of root, right? So if we take just this kind of polynomial here, for example, then in order to describe all of its roots, we need to take the square root of x1 to the third plus x2 to the third. We have to add this kind of element. And this is what we're calling an integral homogeneous element. So it's just an element of, we can say, of the algebraic closure of Cx, which satisfies some very close relation like this. So just as this polynomial here, where this gamma is a weighted homogeneous. So it's homogeneous, but maybe with weights depending on the different entries x1, x2, y. And we can always take it, given a gamma, we can always take it minimal. So we can always take it irreducible. So when we're going to talk about constraints, we're going to talk really about being constrained, the roots being constrained because they're related to this very specific kind of homogeneous polynomial. The roots are going to be related by this kind of polynomial. Now the notion of the ring that we are searching, and that we have to justify later on that it does work, is called the projective ring that we're going to work. So given H, any homogeneous polynomial, and gamma, some integral homogeneous element, just as before, the one that satisfies this weighted homogeneous polynomial, we're going to denote by pH, like this, the subring of the valuations, where the elements have this nice looking form. So the divisors of it are all related to this same H. So this ring certainly is going to give us information about all of the, after one blowing up, about generic points of the exceptional divisor. The only points where it doesn't give us information is over the strict transform of H equals 0. At all of the points, we're going to describe all of the power series rings that we are interested in. And even more, if we want to look really at the elements of the factors, we're going to look at the pH x gamma. So now we're just going to add elements of this form here. So D depends, it's something that depends on the degree of gamma, depends on the degree of this polynomial here. But without entering details, it's just some sum where this AK of X are in the previous kind of ring, and this gamma, so that the valuation here is positive, sorry, and this gamma is one of this integral homogeneous ring elements that we looked at before. And the first result that justifies our choice to look at this kind of ring is the following, which we are calling Newton-Puiseux-Eisenstein factorization. So given the P, some monomial polynomial in this kind of ring, there exists some homogeneous element gamma and an homogeneous polynomial H, such that P does factor as we wanted, as factors Qi, where these Qis are the pH. This is the ring that we were searching for, and that we have to justify that it satisfies all the properties that we want. So in particular, irreducible even in the evaluation ring itself. Moreover, when I factor each one of the Qis, I can factor them in this polynomial that I added the homogeneous element. And for each one of them, when I fix I, for each one of these roots, I can obtain one from another by replacing gamma by one of its conjugates. So all of the roots, they are going to be related by this homogeneous, the weighted homogeneous polynomial, which actually can be assumed to be reducible because they are all, it's conjugate, so they are all part of the same, they are all related by a minimal weighted homogeneous polynomial. So this is going to give us the constraint that we were searching for. Okay. Now the next step that we have is to give a notion of convergent projective rings. So we're going to denote by pH x a subring of the this projective ring that we looked at, characterized by the following. Given an element like this, we're just going to take the ones that the sum of the numerators are actually convergent. Now, two remarks about this. The first one is that if I do this, then every time that I'm not over the strict transform of H equals 0, the pullback of this series is going to be convergent. So if I have an element here and I pull back by the blowing up, I'm going to be convergent over sets like this. So I'm going to avoid H equals 0, and I have to avoid other exceptional divisors. But I'm going to be convergent as everywhere else. The second remark is that this is, it's not clear that this definition is well defined, because for an element A, there are many ways to denote this sum. So it's surprisingly subtle to prove that it is well defined, but it can be done. You use it to a complex analysis. You have to modulate things and play with it a bit. It's not simple, but with complex analysis, it can be done. This is the remark. So I have two more slides. Let's try it. So the first result that I want now is that I had this factorization that I want to in terms of this QIs. And the first thing that I want to show is that if I have one convergent factor, then one of these elements of this factorization is going to be in this projective convergent ring. So this is what it's saying. We are in this overarching framework. We suppose that there exists a point there where PC admits a convergent factor. We want to show that one of these factors coming from this projective rings, they are actually convergent, that above notion. Now this is not trivial because these are factors along the divisor. They cannot be reduced along the divisor, but along a point they can. So in the point C itself, it might be that when I localize at C, the QIs, they factor. And the only thing that we know by hypothesis is that one of these Rij's, they are convergent, but not all of them. So we have to show that from one of them is convergent, all of them related to one of these QIs is also convergent. And the key point here is, again, that we have enough constraint for that. So we do know that this QI belongs to, the roots of QI belong to the projective ring joined with gamma. So they are linked by an irreducible weighted homogeneous polynomial. And then by using an argument that we learned from a paper of Izumi, we are able to show that if one of them is convergent, then we can show that all of them are convergent. By using a little bit of subharmonic complex analysis, we can show that. Okay, so one of these QIs now is in this ring. What is missing now is to be able to say what happens at these points where H equals 0, or when we have another exceptional divisor. And now, what we're going to show, the last point of the proof, is that since all of these Q's, they are, when I take the product, they are equal to this P, so they are actually convergent. So from this information, we're going to show that these polynomials, they do extend formally at every point, especially in the points where H equals to 0. So extends formally is exactly what we think that it should mean. The composition actually belongs, it has a representative which actually belongs to the formal power series. And furthermore, if it is convergent in the projective region which is convergent, then the extension is actually analytic. So just a couple of words about the proof of this result. The first thing is that this result here, and with this we finish the proof, right? Because now we have these extensions and we prove that the ring that we are searching does exactly what we wanted to do. It does capture this convergent factors along the divisors. So the two remarks are the following. The first thing is that even if P is analytic, this theorem is not trivial, because we are saying that we are able to capture all of the factors along the divisor a priori. So this is not trivial. But we can prove it in an easy way by basically combining two results. So a Bianca-Young allows us to know how these roots behave close to H equals to 0, and by analytic continuation. So it's going to be convergent like this. And by analytic continuation, by Bianca-Young, I have a description over here. And by analytic continuation, I am able to say that all of these QIs, they have to extend to the last point. Now, the formal case, which is the case that we need, we do have a Bianca-Young, but we don't have analytic continuation. So what we do is that we use Artin approximation theorem in an argument that already appeared appears already in a certain degree in Gabrielov's result. So we use Artin approximation to find a sequence of convergent polynomials that converge to the formal one. And then we just have to choose this sequence well enough and to prove results about the convergence of the factors to show that the factors of this sequence of polynomials also converge to the factors of P itself. So we do this kind of approximation result. And with this, I will finish the talk. So thanks a lot for your attention.
Well, thank you very much. Well, you have certainly convinced me that the proof of this theorem is pretty difficult. Even your version.
Oh.
But yeah, that looks like a difficult task to tell in 1 hour or 50 minutes. So are there any questions, comments?
I have a question. Does it make sense to look at a ring of Puiseux power series?
It does. It does look. This is related to this theorem here, right?
Right. Can you like define a rank also there, and what is the rank going to be?
The ring of
the Puiseux power series. So instead of working in formal power series, working in Puiseux power series. Does it make sense?
Right. So I just want to. So basically, I want to work. But do I want to work in the ring with x to the power 1 over k, for example?
Right.
Or do I want to? But I want to have some sort of bound of it, or do I want to work with no bounds over the k?
No bound.
No bounds. So like in the positive characteristic case, then in that situation, I'm not completely sure. I think it makes sense, but the person that I would like to ask this question would be my collaborator Guillaume, because he does work also with the positive characteristic case, and therefore he does work with this.
No, you work in zero characteristic case, but you look at Jordan in Puiseux power series.
Okay.
Yeah. So can you find rank? And is rank the same as formal or analytic in this case?
I guess so. Yes, I can define the same thing. Yes.
And is it going to coincide with formal rank or with analytic rank, or with a generic rank?
I can define at least analytic rank and formal rank in an easy way, I guess. The generic rank, probably true. Yeah. If I'm going from
you define it. So if you look at Puiseux power series and define a rank there, it's going to coincide with usual analytic rank or generic rank or formal rank. Or it's different rank.
The usual rank that we mean is the one coming from the Jacobian.
Right.
Then it should be the generic rank.
Okay.
Sorry, I'm not sure I can answer the question precisely.
No, just a question about what in the Puiseux power series, what happens.
Fair enough. I don't know how to answer it at this moment.
Okay.
Sorry.
I'm not sure how to.
I prefer to say that I don't know than to say something that is wrong, actually. That's my position here. So maybe we could discuss afterwards. But,
yeah, we can try.
We can try, yeah. Maybe by email.
Yeah, by email.
Okay.
Any other questions?
Yeah, I have a comment. I think the strategy of this proof was really very well explained. I wanted to mention there's a really wonderful theorem of Pavoutsky, which says that given an analytic morphism, the set of points in the source where it is regular in this sense of Gabrielov, that the three ranks coincide, the set of regular points is a closed analytic subset of the source of the morphism. Pavoutsky's proof is, in some sense, a parameterized version of the proof of Gabrielov. And I would say that if Gabrielov's proof is difficult, Pavoutsky's is completely impenetrable. And I think it would be really great to get a grip on Pavoutsky's result in understandable terms.
Thanks a lot. This is indeed it's something that had told me already in another conversation, and it's actually something that we are doing now. We're trying to do it now. It seems that a lot of the techniques that Pavoutsky used does translate well to the language that we use too. So I'm hoping that we're going to be able to do so.
Okay, any other questions? Well, if not, then let's thank the speaker again. Applaud with your hands or with